In 1876, inside a Philadelphia exhibition hall, 100,000 people stood next to a machine nobody warned them about. A 30-foot cast-iron flywheel, 56 tons, spun at the center of the largest building most of them had ever entered, with no barrier between its rim and the crowd. President Ulysses Grant started it. The Emperor of Brazil watched it turn. But in 6 months, 10 million Americans walked past it without once asking what would happen if it broke. This is the story of the Corliss Centennial Engine and the dangerous secret it was holding the entire time. If these stories about the machines that built America are something you enjoy, I would really appreciate it if you could subscribe and let me know in the comments which machines or industrial disasters from this era you want me to cover next. Now, back to Philadelphia. To understand what made the Corliss engine so significant, you have to understand the world it came from. In the 1870s, there was no such thing as an individual electric motor attached to a single machine on a factory floor. Every lathe, every loom, every press, and every pump in a manufacturing building ran off a single source. A large, central steam engine sat in an engine room at one end of the facility, and its power traveled across the entire floor through a system of overhead rotating steel shafts. From those shafts, hundreds of leather belts dropped down to every individual machine below. Those leather belts were moving fast, at the speed of a galloping horse. Workers who maintained the overhead shafts and belt drives walked through spaces where moving machinery passed at head height. A belt catching a loose sleeve did not give you time to react. A belt, snapping under full tension, crossed the room before anyone could shout a warning. But the belts were not the most dangerous part of the system. At the center of every steam engine in every American factory was a flywheel. A massive cast-iron wheel spun on the main shaft, and its job was to smooth the power delivery from the engine. Steam pistons fired in pulses, each stroke surging then falling, and a textile mill running dozens of looms that uneven motion snapped threads and ruined product. The flywheel absorbed each pulse and released energy between them, keeping motion smooth and the machines running at a consistent speed. The heavier the flywheel and the wider its diameter, the more energy it stored in the rotating rim. A flywheel running at standard factory speeds held energy that engineers of the era compared to industrial boilers at full pressure, not in heat, not in fire, but in pure stored mechanical force. Tons of cast iron moved at 45 miles per hour, and yet from the outside it appeared almost calm. Cast iron has a property that steel does not. Steel bends and deforms under stress, stretching and giving warning before it fails. Cast iron holds its shape all the way up until the stress exceeds its tensile limit, and at that point it does not crack gradually. It shatters all at once. A flywheel rim that shatters at operating speed does not fall to the floor. Each section continues traveling in the direction it was already moving when the fracture formed. Engineers who investigated flywheel failures during the 1880s and the 1890s found iron sections weighing several hundred pounds embedded in the ground outside factory buildings. They found fragments that had punched through 2 and 3 foot thick brick walls. They found debris scattered more than the length of a football field from the original engine room. Could you imagine working beside one of those spinning cast iron wheels every day of your working life? Let me know in the comments. What made the flywheel particularly insidious inside an American factory in the 1870s was how calm it looked during normal operation. A wheel 30 feet across, spinning at speed, produced almost no sound of its own beyond a low, consistent hum that workers stopped hearing after the first week on the job. The motion was smooth, the rotation steady, and nothing about the visual appearance of the machine communicated the forces stored in the rim. Investigators who studied flywheel accidents in this period consistently noted that the failures came without visible warning. No wobble, no preliminary cracking sound, no vibration the floor crew reported noticing before the rim let go. The machine simply ran until it did not. The men who tended steam engines and maintained flywheel shafts in American factories during this period were the best paid workers in the plant. Everyone understood the reason for the premium. Their job was the most likely to kill them. What a shift inside one of those engine rooms actually looked like is worth dwelling on. The men worked 12 hours at a stretch, 6 days a week, inside a room dominated by a spinning cast iron wheel as tall as a house. The noise was constant, a deep mechanical rhythm you felt in your chest more than you heard with your ears. The heat from the boiler fire radiated through the engine room walls throughout the shift. Workers who maintained the belt drives moved through narrow walkways where a leather belt 15 inches wide ran at head height. One misstep toward that belt was a decision you did not survive, but the physical danger was only part of what made the job what it was. The other part was the knowledge. The men who ran those engines understood, in a practical way that no engineering textbook described, what the flywheel beside them was holding. They had seen what happened in other mills. The stories traveled through the trade, a wheel letting go in Pennsylvania, fragments through the wall. Men who never made it home. But they went back to work the next morning because the alternative was not getting paid, and not getting paid had consequences too. By 1876, American factories had been running on this central engine system for decades, and the machines had been growing larger every year. Mills in Lowell, Massachusetts, in Paterson, New Jersey, and in the steelworks of Pittsburgh, Pennsylvania, had central flywheels that weighed 20, 30, even 50 tons. A heavier rim stored more energy. More stored energy meant the engine could absorb sudden load changes without stalling, and more stability meant more output per shift. The risk grew at the wheel, and nobody stopped the growth. That is the world. George Henry Corliss was working inside when the organizers of the 1876 Centennial Exhibition came to him. Corliss ran a manufacturing operation in Providence, Rhode Island, and by the mid-1870s, he had a reputation that few American engineers could match. His name was attached to a specific steam valve design that controlled how steam entered the cylinder more efficiently than anything else available at the time. Corliss engines had been running in New England textile mills, in Pennsylvania steel works, and in factories across the industrial Northeast for years. Factory owners specified them because they worked and kept working. What the exhibition committee asked him to build was something he had never attempted, and no one else had attempted either. A single engine capable of delivering power to every machine in Machinery Hall simultaneously, running reliably 7 days a week for 6 months, in front of an international audience that included heads of state, foreign engineers, and journalists from every major publication in the world. Corliss agreed to build it at his own expense. His one condition was that the exhibition committee return the machine to him when the fair ended. He was not doing this for a contract payment. He was doing it because it was the most ambitious steam engine anyone had ever attempted, and he intended to be the one who built it. The engine took shape at his Providence works over 2 years. 2 vertical steam cylinders, each with a 44-inch bore, drove a single crankshaft mounted at the top of the central structure, and that crankshaft connected directly to the flywheel. The flywheel was 30 feet across and weighed 56 tons. Because no foundry could cast a wheel that size in a single pour, it was built in sections and bolted together at the rim, each joint a point where rotational stress would concentrate in ways the engineering of that era could not fully calculate. The total assembled weight of the engine was 700 tons. At operating speed, the rim of that flywheel traveled at 66 feet per second. That is roughly 45 miles per hour. Not the center of the wheel, the outer edge of a 56-ton casting. The nearest visitor walkway inside Machinery Hall was within 30 feet of that rim, and the building's walls were stone and brick, designed to hold weight and keep out weather, not to stop sections of cast iron traveling at highway speed. Corliss had done his calculations, had inspected every casting, and was confident the iron was sound. He was right. But we will come back to what right and safe actually mean in practice, because they are not the same thing. Now, let me take you to opening day. The United States was 100 years old in 1876. The country had survived a civil war barely a decade earlier that killed more than 600,000 people, and the economy and national mood were still finding their footing. But in the industrial cities of the Northeast and Midwest, there was something the country could point to with confidence. American manufacturing output had grown faster than any other nation since the war ended. American railroads had connected the continent. American machine shops were producing equipment that was beginning to compete seriously with the best manufacturers in Britain and Germany. The 1876 Centennial International Exhibition in Philadelphia was the public answer to all of that. 186 nations participated, 30,000 exhibits spread across 5 enormous buildings covering nearly 300 acres of Fairmount Park. The Centennial drew visitors from across the country and the world. Machinery Hall was the building that mattered most. 13 acres under one roof, filled with actual working industrial machinery from every participating nation, all of it running continuously. Looms throwing shuttles, lathes cutting metal, print presses producing full-size newspapers that visitors could take with them as they walked past. The entire industrial output of the modern world running simultaneously inside one building, all of it drawing power from one engine and one flywheel. I want you to actually picture what it felt like to walk into that building. The noise alone would have been unlike anything most visitors had encountered in their lives. A layered mechanical roar where individual machines were indistinguishable from the combined sound of all of them running at once. The air smelled of machine oil and heated metal and coal smoke. Leather belts slapped overhead. Floors vibrated. Workers moved through the machinery with the practiced ease of people who had learned to treat that environment as normal. And standing at the center of it all, driving every machine in 13 acres simultaneously, the flywheel turned. On May 10, 1876, Grant and Dom Pedro II, Emperor of Brazil, stood at the starting levers of the Corliss engine in front of 100,000 people. They moved the levers together. Steam entered the cylinders, the crankshaft turned, and the flywheel began to rotate. Power moved through the main shaft the length of Machinery Hall, and out through hundreds of leather belts to every machine on the floor. Witnesses in the hall described the sound as a rising mechanical wind that filled the entire building from one end to the other. The floor vibrated. Workers at the printing presses began feeding paper immediately, and freshly printed newspapers were being handed to visitors within minutes. Dom Pedro, according to accounts published in Philadelphia newspapers the following day, stood from his chair and said the machine was astonishing. He had supervised major industrial operations in South America and toured the best factories in Europe. He had never seen anything like this. Now, here is what nobody said out loud that morning. If you are finding this as fascinating as I do, hit subscribe right now so you do not miss the next video in this series. I cover a new forgotten machine or industrial story every week. The flywheel was turning with no enclosure around it, no housing over the rim, and no barrier between the 56-ton spinning iron and the 100,000 visitors who were standing inside the same open space. It was a cast iron wheel in bolted sections, its rim turning at 45 miles per hour. The people who had traveled from every state in the country to see the future of American industry were standing within effective range of it, without knowing that was where they were. Corliss knew what the wheel was storing. His engineers knew. They had done the calculations, and they were confident in the iron. Their confidence was earned because the engine ran for 173 operating days without failure. In June of 1876, about a month after opening day, Alexander Graham Bell set up his electrical equipment inside the exhibition's electrical section and ran a wire across the room to a receiver. Dom Pedro, who had returned to the fair specifically after hearing reports of the new device, held the receiver to his ear. Bell spoke into the transmitter from the far end of the wire. Dom Pedro stood upright and said out loud that the thing talks. That demonstration became the moment the telephone entered American public consciousness. Every major newspaper in the country reprinted the story within days. The telephone went from an inventor's experimental device to something the Emperor of Brazil had heard with his own ears in front of witnesses. But all of it happened inside the same building, under the same roof, powered by the same flywheel that was spinning 30 feet from where the visitors stood. But here is what I cannot stop thinking about. Being right about a calculation is not the same thing as being safe. It means the particular casting happened to be sound. It means the bolted joints in the rim happened to hold their tension for 6 months under continuous rotation. It means the mechanical governor that controlled engine speed happened to function within limits throughout the entire season. The machine got lucky, and the 10 million people who walked through that fair got lucky along with it. There were other flywheels in other mills where the casting was not sound. Those stories end differently. Engineering journals published in the United States and Britain throughout the 1880s and the 1890s document multiple flywheel failures in textile mills and manufacturing plants, in formal technical reports written by inspectors and engineers after on-site investigations. In a documented Pennsylvania mill failure, iron drove through the exterior wall of the engine house and was found embedded in the yard outside. In a separate English incident, sections weighing over half a ton were thrown through masonry walls and recovered hundreds of feet from the machine. In 1891, 15 years after the Centennial Exhibition, a flywheel at the Amoskeag Manufacturing Company in Manchester, New Hampshire shattered during normal operations. 3 workers were killed instantly. Iron fragments punched through the brick walls of the engine room, heavy sections scattered across the mill yard, and damage was recorded in 4 separate buildings beyond the engine house itself. The Amoskeag Works was one of the largest textile manufacturing operations in the world at that point, employing thousands of workers. And the failure happened on an ordinary shift, with no warning that anyone who survived the event could later describe. The Amoskeag flywheel weighed 56 tons, the same weight as the flywheel that 10 million Americans had walked past in Philadelphia. Think about what that means. The machine that killed 3 men in Manchester, New Hampshire was the same weight, the same material, the same era, and the same design as the machine that Grant and Dom Pedro had started in front of 100,000 people. The difference between those 2 outcomes was not better engineering or superior iron. The difference was that one casting happened to be sound and one did not. And the people at the Amoskeag Works in 1891 who did not survive their shift that day were doing the same job under the same conditions, beside the same type of machine that the workers at Machinery Hall had done every day for 6 months in 1876. The only meaningful difference was which mill they worked in, which foundry had poured their particular wheel, and what invisible flaws that pour had introduced into the iron. In an era before X-ray inspection or materials testing, there was no way to know which side of that line you were on until the machine told you. The exhibition closed in November of 1876. Corliss had the engine disassembled and the components shipped to Chicago, where it was sold to the Pullman Palace Car Company, the manufacturer of the sleeping railroad cars that made long-distance travel comfortable for Americans with the means to afford a berth. The engine was reinstalled at the Pullman Works on the south side of Chicago. The flywheel that President Grant had started now turned inside a production facility driving the equipment that built railroad cars, with nobody writing a word about it. The most famous machine in America in 1876 was running production shifts in a Chicago factory by 1878 and had been entirely forgotten by the public. It ran in the Pullman Works for years, alongside workers who likely had no idea what they were looking at. But in the first decade of the 20th century, individual electric motors began replacing central steam plants across American manufacturing because smaller distributed motors were cheaper to run, simpler to maintain, and when one failed, one machine stopped, rather than an entire building going dark. The Corliss engine was removed from service. Sometime in the early 20th century, the 700-ton machine that had been started by the President of the United States, that had powered Alexander Graham Bell's first public telephone demonstration, and that had run for 6 months as the centerpiece of the greatest gathering in American history to that point, was scrapped for the iron. There was no newspaper account of its last day, no public ceremony, and no record anywhere of the exact date the scrapping was done. Machinery Hall had already burned down in 1876. A fire that destroyed the building shortly after the fair closed. The grounds were absorbed back into Fairmount Park. The stone foundation that had anchored 700 tons of engine was eventually covered with grass. 10 million people saw what American industrial technology looked like at its peak in 1876. They went home to every corner of the country, and the industrial future followed them. The United States became the largest manufacturing economy in the world within 30 years of that exhibition. Whether the fair caused that trajectory or simply documented a moment already underway, historians still argue, and I will not pretend to settle it here. What those 10 million visitors carried home with them, beyond the printed newspaper from the machinery hall presses and the memories of the telephone demonstration, was a specific image. A machine so large it powered an entire building, running without stopping, controlled by two men moving small levers, making the future look as inevitable and orderly as the flywheel turning at its center. They had no reason to think differently. The flywheel had run for 6 months without incident, the math had held, the iron had held, and nothing in the exhibition told them anything about what it would have looked like if it had not. What stays with me is the other part of that story. The workers who tended steam engines and maintained flywheel shafts in American mills during the 1870s and 1880s. The men who worked 12-hour shifts beside unguarded spinning, cast iron in the mills of Lowell and Patterson in Pittsburgh. Most of them have no memorial. The flywheel failures in Pennsylvania and New England, the belt accidents in textile mills, the boiler explosions in foundries, those events are in engineering journals and insurance records if you look hard enough. But the names of the workers who died in them rarely made it past the local newspaper, and most of those papers are not digitized, not searchable, and are just gone. The machines they ran are gone too, melted down for the iron that built the next generation of industry. But the rule those machines taught, the rule paid for in the lives of men whose names we do not know, that rule is still with us. The Corliss engine was lucky. It held for 6 months and became famous, but was forgotten and became scrap with no more ceremony than any other worn-out piece of factory equipment. The men who were not lucky are simply gone from the record. That is not an accident of history. It is a feature of how the industrial era recorded itself. Company ledgers tracked production. Engineering journals tracked failure modes in the aggregate. Newspapers covered disasters large enough to warrant coverage. Individual workers, the men who showed up at the mill in Lowell, at the steelworks in Pittsburgh, or in the engine room in Manchester, appear in the historical record only as numbers. Injuries per 1,000 workers, fatal accidents per year of operation. The men behind those numbers mostly do not have names anyone can find. What the steam age ultimately taught the industry, at the cost of those men, was a rule that still shapes how dangerous machines are built today. If energy is stored in one place, the risk concentrates in that place. If a machine can fail catastrophically, the space around it has to be designed for that failure. If you put 100,000 people next to a spinning flywheel, someone should ask what happens if it breaks. It took decades and a great many lives before that question was taken seriously. Thanks for watching.